You see green curtains dancing overhead. You watch purple and red waves ripple across the night sky. You stand there under the aurora borealis, and you think you understand it. Solar wind, magnetic field, particles hitting the atmosphere. But nobody talks about the quantum secret buried in every photon of light. The forbidden transition that shouldn't happen, but does. The electron trapped between energy states for almost 1 full second. The atomic oxygen that splits and waits and finally glows at exactly 557.7 nanometers. Where does that green come from? Why does red appear only higher up? What quantum rule breaks to make this cosmic dance possible? They were all looking at the same phenomenon. But the real story sits in electron shells and transition probabilities. The quantum machinery that transforms solar violence into visible beauty operates on timescales measured in nanoseconds and rules written in the language of forbidden spectroscopy. That superheated plasma doesn't stay contained. Charged particles, protons, and electrons stream outward in what Richard Carrington first suspected back in 1859. He watched a solar flare on September 1st of that year. The next day, Earth's magnetic field went haywire. George Fitzgerald later proposed that matter was being accelerated away from the sun, reaching Earth after several days. They were right, but they didn't know the quantum details. These aren't gentle breezes. A single CME can hurl billions of tons of plasma toward Earth. The May 2024 event, tracked by active regions numbered 13664 and 13668, produced an X 2.2 flare on May 9th. That CME caught up with a slower one from May 8th. They merged. They hit Earth simultaneously. The result was the strongest geomagnetic storm in 20 years. If you value documented quantum mechanics and atmospheric physics like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from Nature Physics, published December 3rd, 2025, discussing auroral color mechanisms, and Geophysical Research Letters, August 2024, documenting Earth's magnetosphere, interactions during CME impacts. These aren't pop science articles. These are peer-reviewed papers with spectroscopic data and transition probability calculations. Now back to the information. The wind curves around it, stretching the field into a windsock shape with a long tail on the night side. Normal solar wind just flows around, but during CME impacts, something changes. The bow shock can temporarily disappear. Plasma and magnetic field from the sun interact directly with the magnetosphere. In April 2023, researchers documented this in Geophysical Research Letters. Earth's usual tail vanished. Structures called Alphen wings replaced it, connecting Earth's magnetosphere directly to the erupted region of the sun, a highway for plasma. Energy coupling between solar wind and magnetosphere depends on wind velocity and the interplanetary magnetic field clock angle. When that angle exceeds roughly 45 degrees, energy input increases dramatically. Earth's magnetic field lines converge there. Electrons from the magnetotail spiral downward along these field lines. They're traveling at significant fractions of light speed. Some carry energies from 100 electron volts to 30,000 electron volts. Others push beyond that. When they penetrate deep into the tenuous upper atmosphere, the thermosphere and ionosphere, collisions begin. This is where quantum mechanics takes over. Earth's atmosphere is 78% nitrogen, 21% oxygen, 1% everything else. But up high, things change. The Kármán line sits at 100 kilometers above sea level. Below that, molecular oxygen dominates. Above it, ultraviolet light from the sun splits oxygen molecules into individual atoms. Atomic oxygen becomes the main component. This matters because atoms and molecules have different quantum rules. An electron smashes into an oxygen molecule at 110 kilometers altitude. The collision transfers energy. The oxygen molecule splits. 2 atomic oxygen atoms fly apart. But these aren't ordinary ground state atoms. The collision has excited their electrons to higher energy levels. In quantum mechanics, electrons occupy specific energy states defined by quantum numbers. They can't sit between these states. They jump. The oxygen atom now has electrons arranged in what spectroscopists call an unstable configuration. The technical term is the 1s state, specifically the 1s0 configuration, where total electron spin equals 0 and total orbital angular momentum equals 0. It's highly energetic. The atom holds roughly 4.2 electron volts above ground state. It wants to relax. Under normal quantum mechanical selection rules, certain transitions aren't allowed. Electric dipole radiation, the usual way atoms emit light, requires specific changes in angular momentum and parity. The selection rules state that orbital angular momentum must change by plus or minus 1 unit, and parity must flip. The transition from oxygen's 1s state to the 1d state violates these rules. It's forbidden by electric dipole selection criteria, but forbidden doesn't mean impossible. It means slow, very slow. The transition can proceed via magnetic dipole radiation instead, a much weaker mechanism. Compare that to allowed electric dipole transitions. which happened in nanoseconds with Einstein. A coefficients reaching 10 to the 8th power per second. This oxygen atom, excited to the 1s state, sits there for about 1 second before emitting a photon. 1 second might sound short to you standing in the cold watching aurora, but for atomic processes measured in nanoseconds, it's an eternity. In that time, at ground level atmospheric pressure with roughly 10 to the 19th molecules per cubic centimeter, the excited atom would collide with dozens of other particles. Each collision could steal the energy away through non-radiative quenching without producing light. The transition would never complete. This is why you can't see this green light in a laboratory on Earth's surface. The air is too dense. Collisions dominate. But at 100 kilometers up, the story changes. The atmosphere is thin. Particle density drops to 10 to the 12 per cubic centimeter. It's almost a vacuum by ground standards, though still dense compared to interplanetary space. Atoms are separated by large distances. Mean free paths stretch to meters or tens of meters. An excited oxygen atom has time. It sits in the 1s state. It waits. And then, without colliding with anything, it finally relaxes down to the 1d state. The energy difference between these two quantum states equals exactly 2.25 electron volts. That energy gets released as a photon. Energy equals Planck's constant times frequency. The frequency converts to wavelength, 557.7 nanometers. Green light, the most common auroral color humans observe. The quantum mechanics here are precise. The transition involves a magnetic dipole interaction, not the usual electric dipole. The transition probability was calculated using multi-configuration atomic models that account for electron-electron correlation. Researchers published these calculations in the Astrophysical Journal in May 2013. They found the ratio of transition probabilities between the green line and the ultraviolet line at 297.2 nanometers equals approximately 9.8. This ratio is a quantum mechanical constant. It doesn't change. Observations from satellites, rockets, and ground-based instruments all confirm it. When you see aurora, you're watching forbidden quantum transitions happen in real time. Green dominates between 100 and 150 kilometers altitude. But look higher. Above 150 kilometers, sometimes pushing to 300 kilometers, the aurora glows red. Same element, different transition. The oxygen atoms excited to the 1s state can also relax down to the 3p ground state. This transition is even more forbidden. The radiative lifetime stretches to almost 2 minutes. At lower altitudes, collisions would kill this transition instantly. But up high, where the atmosphere is even thinner, excited oxygen atoms have enough time. They emit red photons at 630.0 nanometers and 636.4 nanometers. The longer the radiative lifetime, the thinner the atmosphere must be to avoid quenching by collisions. The 1s to 3p transition takes up to 120 seconds. That requires extremely low collision rates, so red aurora marks the upper boundary where the atmosphere is thin enough for this ultra-forbidden transition to complete. Green marks the middle zone. Below about 100 kilometers, collisions dominate and neither transition happens efficiently. This ionized nitrogen can emit blue and purple light through specific electronic transitions. The wavelength 427.8 nanometers produces the blue you sometimes see low in the aurora, coming from the first negative band system where ionized nitrogen transitions from B2 sigma U plus state down to X 2 sigma G plus ground state. Ionized nitrogen can also contribute to red emissions at lower altitudes through different transition pathways. The interplay between oxygen green at 557.7 nanometers, oxygen red at 630 nanometers, and nitrogen blue at 427.8 nanometers creates the full auroral color palette visible to human eyes in cameras. But here's where it gets even more interesting. Nitrogen doesn't just emit its own colors, it actively helps produce the green oxygen line through energy transfer. When electrons hit nitrogen molecules, they can excite them to a metastable state called N2A 3 sigma U+. This isn't an ionized state. The molecule keeps all its electrons but rearranges them into an excited configuration. This state lives for seconds before decaying. When an excited nitrogen molecule in this A state collides with atomic oxygen, quantum mechanics allows energy transfer. The nitrogen drops to a lower state. The oxygen atom gets excited to the 1s state. Then the oxygen emits the green 557.7 nanometer line. Researchers documented this mechanism in the Astrophysical Journal back in August 1969, when Meyer, Setzer, and Stedman showed that energy transfer from nitrogen, A state to atomic oxygen, was a major production route for green line emission. Recent studies using the Southampton ionospheric model, published in Annales Geophysicae in January 2023, confirm it. During low-energy electron precipitation events, energy transfer from nitrogen. A state dominates oxygen, 1s production over direct electron impact excitation. Green aurora peaks at slightly lower altitude than blue aurora because the production rate depends on both nitrogen and oxygen densities multiplied together. Both densities decrease with altitude. Their product, the energy transfer rate, peaks lower than pure nitrogen ionization, which depends only on nitrogen density. The panel convened by NOAA, NASA, and the International Space Environment Services predicted in December 2019 that cycle 25 would peak in July 2025 with a smooth sunspot number of 115. This would make it similar to the weak cycle 24, which peaked at only 116, the fourth smallest intensity since systematic sunspot counting began with cycle 1 in 1755. They were wrong. Solar activity ramped up faster than anyone expected. By January 2023, cycle 25 had already surpassed cycle 24 at the same point, showing 12% more daily sunspots. By August 2024, the smoothed 13-month sunspot number hit 156.7. That's already 36% above the predicted maximum. The largest individual month, August 2024, recorded 216 sunspots. On October 3rd, 2024, sunspot region 3842 unleashed an X 9.0 flare, the strongest of the cycle at that point. Just 2 days later, it followed with another massive release. On October 15th, 2024, NASA and NOAA officially announced solar maximum had arrived. The peak might have already passed somewhere between August and November 2024, or it might extend into 2025 with a possible second peak. We won't know until we have 6 months of declining data to confirm the true maximum. Some solar cycles exhibit double maxima, a phenomenon called Gnevishov gap, where two peaks are separated by a dip. Solar cycle 25 might be showing exactly this pattern. During solar maximum, more CMEs, more energetic particles, more auroras at lower latitudes. The May 2024 storm pushed aurora sightings as far south as northern Europe and parts of the United States. People in places that rarely see aurora got their first glimpse. The magnetosphere compressed. Satellite observations revealed increased fluxes of high-energy particles. Periodic magnetic field fluctuations accompanied particle injections. Geostationary satellites recorded the changes. The storm sent strong electric fields and high-energy auroral particles from the magnetosphere into the polar upper atmosphere along geomagnetic field lines. Joule heating caused localized warming. Global atmospheric circulation changed. An oxygen atom excited to 1s will emit green light at 557.7 nanometers, whether the storm is weak or strong. What changes is the number of atoms getting excited. More energetic electrons mean more collisions. More collisions mean more excited states. More excited states mean brighter aurora. The quantum machinery scales with input energy, but the fundamental transition probabilities remain constant. Spectroscopy reveals this. The auroral green line is an atomic oxygen emission from the O1D2's -1s0 transition. The blue line is a feature of ionized molecular nitrogen. Despite coming from species with different number density altitude profiles, the green and blue auroral emissions peak at surprisingly similar heights. Tens of thousands of camera images analyzed in the Lapland region between 2000 and 2007 showed the typical peak emission height for both green 557.7 nanometer aurora and blue 427.8 nanometer aurora sits around 114 kilometers. Green peaks at 113.8 kilometers, blue at 113.5 kilometers. When emissions peak below this typical height, they peak at very similar altitudes, with green very slightly, about 1 kilometer above blue. When they peak at higher altitudes, blue usually peaks above green. At higher altitudes, energy transfer from nitrogen A dominates. The correlation between nitrogen ionization rate and green line production creates the altitude coupling. Flow. Substorms inject plasma sheet ions and electrons into the inner magnetosphere. Field-aligned currents carry energy down into the night-side auroral oval. Bursty bulk flows transport ring current ions. The entire magnetosphere-ionosphere system couples electromagnetically, but at the bottom of this chain, individual atoms undergo quantum transitions, governed by selection rules established over a century ago. Werner Heisenberg formulated quantum theory while scrambling over Helgoland's rugged cliffsides 100 years ago. His matrix mechanics, combined with Erwin Schrödinger's wave equation, gave us the tools to understand electron behavior. Paul Dirac extended the framework. By the 1920s, physicists understood that atoms could only transition between discrete energy levels. Forbidden transitions, those that violated selection rules, were recognized as real but rare events. Max Planck had started it all in 1900 with his investigation of the ultraviolet catastrophe. He proposed that radiated energy came in discrete quantized packets he called quanta. It was supposed to be a mathematical trick. It turned out to be fundamental reality. Planetary nebulae glow with forbidden oxygen and nitrogen lines. Interstellar gas clouds emit them. The term forbidden is misleading. These transitions happen. They're just slow compared to allowed ones. In high vacuum conditions, like space or Earth's upper atmosphere, metastable states have time to decay radiatively. The phrase highly improbable would be more accurate, but forbidden stuck. When you see O2 in square brackets at 372.7 nanometers, that's forbidden oxygen. O3 in brackets at 495.9 and 500.7 nanometers, forbidden again, and 2 in brackets at 654.8 and 658.4 nanometers, forbidden nitrogen. These lines are common in astrophysical plasmas precisely because space provides the low-density environment where forbidden transitions can complete. Nitrogen emissions are blue if the atom regains an electron after ionization, and red if the atom returns to ground state from an excited state. Oxygen is unusual in its return timing. It can take 3/4 of a second to emit green light, and up to 2 minutes to emit red. These aren't guesses. These are measured radiative lifetimes, confirmed by laboratory spectroscopy, satellite observations, and quantum mechanical calculations. Temperature matters less than you'd think. The thermosphere where aurora occurs has kinetic temperatures reaching 1,000 degrees Celsius during geomagnetic storms. But temperature is just average kinetic energy of particles. It doesn't directly determine emission wavelengths. Quantum energy levels do. The energy difference between oxygen 1s and 1d states equals 2.25 electron volts regardless of ambient temperature. The photon wavelength follows from the Planck-Einstein relation. Energy equals Planck's constant times frequency. Frequency equals speed of light divided by wavelength. Everything connects. A camera sensor gathering light for 10 or 30 seconds captures far more total photons than your eye can. In the fraction of a second, it integrates visual information. Human vision integrates over roughly 50 milliseconds, 1/20th of a second. Beyond that, the brain stitches together a flowing perception but doesn't accumulate signal. A camera with 10-second exposure collects 200 times more photons from the same scene. This dramatically improves signal-to-noise ratio and reveals fainter structures. Second reason, color sensors in human eyes don't work well in darkness. The retina contains 2 types of photoreceptors. Rods provide high sensitivity, black and white vision in low light. Cones provide color vision but require much more light to function. Under typical auroral brightness, ranging from hundreds to thousands of Rayleighs, your cone cells receive insufficient stimulation. Your vision shifts to primarily rod-based monochrome perception. You see mostly white or pale green curtains, even though the aurora emits distinct red, green, and blue wavelengths. Cameras don't have this limitation. Each pixel measures light independent of neighboring pixels and continues accumulating signal linearly. Color information persists even at low light levels. So a camera reveals vivid greens and reds and purples, while your naked eye sees mostly white or faint green curtains. Both observations are real and valid. Your eye is simply less sensitive and less capable of color discrimination in scotopic conditions. It's a period lasting 1 to 2 years. More sunspots, more flares, more CMEs. The magnetic field at the sun's poles flips during this time. North becomes south, south becomes north. Then activity declines towards solar minimum. The cycle repeats. The average length is 11 years, but strong cycles can be shorter, weak ones longer. Solar cycle 24 was weak, the 4th smallest intensity since regular record keeping began with solar cycle 1 in 1755. Cycle 25 has already exceeded cycle 24 in amplitude. 24, recent months from September 2024 to March 2025 range from 136 to 166. Has the peak passed? Maybe. Solar cycles can exhibit double maxima called Gneveshev gaps, 2 peaks separated by a dip. Solar cycle 25 might show this. We need 6 more months of data to confirm whether the peak occurred in August or if another surge is coming. Forbidden transitions aren't the only quantum weirdness in aurora. Frank-Condon factors determine vibrational transition probabilities in molecular nitrogen. When nitrogen molecules get ionized, they can emit across many vibrational bands. The first negative system, B 2 sigma U plus to X 2 sigma G plus transitions, produces the blue light. The intensities of different vibrational bands depend on the overlap between initial and final state. Vibrational wave functions, that's quantum mechanics at the molecular level. Rotational transitions add even more complexity. Every molecular emission line splits into rotational fine structure. High-resolution spectrometers can resolve individual rotational lines in auroral spectra. It transitions down to the 3p1 state. Because both transitions share the 1s upper level, their intensity ratio is a quantum mechanical constant. Researchers measured it at 9.3 plus or minus 0.5 in 2009. This confirms the earlier value of 9.8 plus or minus 1.0 from 2006. Such good agreement means this ratio can calibrate orbiting spectrometers. It's a 2-point standard built into atomic physics. The intense oxygen emission in summer exceeded daytime emissions in other seasons in both occurrence and intensity. It frequently accompanied supersonic neutral velocities ranging from 300 to 1500 meters per second. This suggests high-energy electrons, 30 kiloelectron volts or more, associated with high-speed solar wind streams, can drive green line emission in regions where collisional quenching should suppress it. The mechanism isn't fully understood. It might involve meteoric charged ice particles creating large electric fields. These open field lines get dragged across the polar cap and stretched into the night-side magnetotail, flux storage. Then, night-side reconnection in the plasma sheet closes the flux. Particles stream down field lines toward Earth. Powerful field-aligned currents flow into the night-side auroral oval. Plasma sheet ions and electrons inject into the inner magnetosphere, into the ring current, into the radiation belts. This is the Dungy cycle, proposed in 1961. Observations confirm it. These standing waves persist longer than traveling waves. They're around longer to accelerate particles in near-Earth space. Impacts on radiation belts, on aurora, on the ionosphere. Research published in October 2021 documented this in detail using models of solar-wind magnetosphere interaction. Even without magnetic reconnection, shear flow between solar wind and magnetosphere can transfer energy through Kelvin-Helmholtz instability. The efficiency depends on solar wind velocity and density. During intense northward interplanetary magnetic field events, when the field points north instead of the usual southward tilt that enables dayside reconnection, viscous interaction and the effect of the field's Y component become the dominant energy. Input mechanisms. Researchers found that when the IMF clock angle exceeds approximately 75 degrees, the Y component effect outweighs viscous interaction. Now the atom waits in the 1s state. The selection rules say electric dipole radiation won't allow a transition down to 1d, but magnetic dipole radiation will, slowly. The atom waits. Approximately 1 second later, it emits a photon, 557.7 nanometers. Green. That's the entire quantum story from the atom's perspective. Everything else, the solar wind, the magnetosphere, the geomagnetic storms, is just the delivery mechanism that brought the energy to excite that particular atom. If you value documented atmospheric quantum physics and space weather science like this, subscribe. Comment what you learned. This script pulls from peer-reviewed sources including Journal of Geophysical Research, Space Physics, published August 2025, on solar wind ion composition, Analysis Geophysicae, January 2023, on auroral emission peaks, and the Astrophysical Journal May 2013 on oxygen. Transition probabilities. These are the actual mechanisms with measured transition rates. Now back to the information. Historical observations struggled to explain this. In 1859, Richard Carrington watched a solar flare. The next day, auroras appeared as far south as the Caribbean. Telegraph systems failed. Carrington suspected a connection. George Fitzgerald proposed solar particles reaching Earth. He was right about particles. The full picture took another 70 years when quantum mechanics arrived. Sidney Chapman and Vincenzo Ferraro developed magnetosphere theory in the 1930s. The space age confirmed their predictions. Satellites mapped the bow shock, magnetopause, plasma sheet, magnetotail. James Van Allen discovered the radiation belts in 1958. Twin toroidal regions trapping high-energy particles. Inner belt from 1,000 to 6,000 kilometers. Outer belt from 13,000 to 60,000 kilometers. These belts breathe with solar wind pressure. The aurora that night was spectacular but costly. The Parker Solar Probe flies through the corona measuring fields and plasma. In December 2024, it approached within 6 million kilometers of the solar surface. Data feeds forecasting models. Rocket experiments probe aurora directly. Sounding rockets measure particle fluxes, electric fields, plasma density. Flight times are brief, but data are invaluable. Incoherent scatter radar tracks, ionospheric parameters continuously. Together, they create the aurora. No step is arbitrary. Everything connects. The hierarchy determines which transitions dominate. Historical aurora records go back millennia. Chinese texts from 600 BCE, Korean Silla dynasty records, Japanese chronicles, European monastery logs. Researchers mine these for past solar activity. Strong aurora at low latitudes indicate major geomagnetic storms. By cataloging historical aurora, scientists reconstruct solar cycles over centuries. Largest geomagnetic storm in recorded history. Aurora visible in the tropics. If it happened today, damage would be catastrophic. Trillions in losses. We've been lucky, but the sun is capable. Oxygen 1s to 1d will always emit 557.7 nanometer photons. The transition probability remains approximately 1 per second. These are fundamental atomic properties depending on universal constants. The aurora's color palette is written into atomic structure. It confirmed the forbidden transition mechanism. It explained the altitude dependence. It described how nitrogen contributions vary with energy. The article synthesized decades of research into a coherent picture. Oxygen atoms in the thermosphere, excited by solar wind electrons guided by Earth's magnetic field, undergo slow quantum transitions that emit characteristic wavelengths. The process is understood. The mechanisms are mapped. The equations work. It's a cosmic laboratory where quantum mechanics, atomic physics, plasma physics, and magnetospheric dynamics intersect. It's space weather made visible. It's solar wind translated into photons by forbidden transitions in tenuous oxygen. Quantum rules say it shouldn't emit this way, but quantum rules also say magnetic dipole transitions are allowed. Slow, but allowed. The atom waits. Then it releases its photon, 557.7 nanometers, green. That photon travels downward through the thin atmosphere. It enters your eye. Your brain processes it. You see green. You're witnessing a forbidden quantum transition, one of billions happening simultaneously. The northern lights, the aurora borealis, quantum mechanics on full display. The quantum transitions continue all the way down. As long as electrons have energy to transfer, atoms will excite. As long as the atmosphere is thin enough, forbidden transitions will complete. The show continues. Energetic particle precipitation creates nitrogen oxides. These wash out of the atmosphere into precipitation. Ice records them. The spikes match Chinese and European aurora records from centuries past. This confirms that major auroral events occurred when texts said they did. It validates the historical accounts. It proves that the quantum transitions we see today happened identically in the past. Oxygen atoms emitted 557.7 nanometer photons in 1300 CE just as they do now. The quantum machinery is timeless.